Hi, I'm Tommaso, PhD at Graz University of Technology.
And I'm Daniel, also a PhD at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
You know, I noticed something about our names I think you might appreciate.
I equally doubt the latter and the former.
Well, mine starts with T, yours with D. In German, hartes T and weiches T. So, our bond is stronger than you thought. Isn't that amazing? A friendship encoded in the alphabet.
Lucky me.
I think building our friendship has been a bit like trying and having metals and polymers stick together. I want a strong bond. You, on the other hand, seem to prefer a bit more of a flexible relation.
You made some terrible puns there, as usual, but I guess you nailed it.
I guess it's good that we haven't just delaminated with time.
I'm quite glad we aren't laminated in the first place.
But anyways, we asked some students and colleagues of ours whether they thought metals and polymers could get along well.
And that is what they had to say.
Polymers are, as far as I know, kind of big molecules made out of a chain of many smaller parts. And I know that they have many everyday applications, such as in electronic devices or in clothing. Sometimes you can attach them to a surface.
I guess a polymer is a sort of plastic. And if they go along with metals, I don't really have a clue. I guess I have a 50-50 chance by saying yes or no. So I'd go with a yes.
Our first thought is that it's like polyamorous relationships, but for like smart people, like physics students, I guess. Do polymers and metals get along well? Do they, Yasmin?
I guess it depends on the polymer. But in some cases, yes. And in some, I probably think no.
As a psychotherapist, I think it depends on what star signs they have.
What kind of relationship it is, if it's toxic or not.
Polymers are materials made of long chains of repeating building blocks or molecules, and an example would be plastics. How well a polymer sticks to or interacts with a metal depends on things like maybe the surface energy of both materials and how they chemically react with each other.
So, today on the show, we have the pleasure of hosting Johanna Byloff, a PhD candidate from ETH in Zurich. Johanna, would you like to introduce yourself, tell us about your field of expertise, your studies? Stage is yours.
Thank you very much. So I'm originally from Vienna. I then went to Leoben to study material science with Daniel. And he went to Graz and I went to Zurich to do a PhD also in materials science. And my PhD topic is called nanoscale engineering of metal polymer interfaces. So you might know what a metal is, what a polymer is, but probably not what nanoscale engineering is. So essentially, we look at the interface between metal and a polymer, and we do it at a very small scale. So 150 nanometers, which is 200 times smaller than a hair.
Could you maybe explain to us what exactly polymer is and how it differs from a metal?
So we use polymers probably more often than metals in real life. Like if you think about packaging or like just any type of consumer stuff, they are usually amorphous and are made up out of chains of covalently bonded carbon atoms. And sometimes you get functional groups with specific properties attached to these chains. In contrast to a metal, you have weaker bonding between those chains. So you usually get a very soft material. So with a metal, it's not amorphous, it's crystalline. This means that you have a periodically arranged structure, and all of these atoms share their electrons in a so-called sea of electrons. And this is why metals are electrically conductive. However, since the bonds are so strong, metals are not as flexible and also much stronger than polymers.
That sounds really complicated to have them talk to one another. And how do you interface the two things? Because they have different properties, right?
This is actually a challenge. So the main process we use is called magneton sputtering. So we apply an electromagnetic field to something called a target. So an aluminium plate. So I work with aluminium. And this then creates, we introduce a process gas into our vacuum chamber. And this gas is then turned into a plasma, which means that the electrons are taken away from our gas ions. And these ions are then accelerated to the metal and knock out metal cations, which then arrive on our substrate. And this way, you can have a very nice uniform metal layer on any sort of substrate. And why do we use this process? We want very small layers, so 150 nanometers. However, since our substrate is a polymer still, our adhesion between metal and a polymer is not optimal.
How do you improve this connection? And I guess this is something you dealt with also.
Exactly. Thank you for saying this. This is exactly my topic. So we use a system, aluminium on polyimide. You might not be super familiar with polyimide, but if you open your phone, I can guarantee you will find this polymer. It's the flexible electronics and space polymer because it already works. So you can sputter aluminium onto polyimide quite well. However, once you bend your substrate or you pull on it, then you will get cracking. So we were actually inspired, when you coat, if you take a bulk sample of aluminium and you spin coat a polyimide onto it. So this is a chemical process where you have some components and then you coat it and then you heat it up. And during this heating process, you actually get a chemical interface between aluminium and your polymer. So it's not only physically bonded, but also chemically bonded, which makes it exceptionally strong for this sort of combination. And we were inspired by this chemical interface and thought, okay, hey, maybe we can also do that. So we introduce a second process called atomic layer deposition, ALD, and use it together with our physical vapor deposition, PVD, to create a strong composite system. So to sum up, we create an interlayer using ALD. We deposit it onto our polymer substrate, and then we put our metal, our aluminium, onto this, and our ALD interlayer improves the properties of the metal polymer system.
Why exactly polyimide and aluminum? Is there any real-life application for this combination?
Yes, we actually got inspired by space applications. So maybe you guys definitely know the Hubble Space Telescope, right? It's no longer in operation. Do you know what replaced it?
I think James Webb, could it be?
Exactly. It's much better, much higher resolution. However, it needs to be protected from the sun because all of the instruments ideally work at 40 to 50 Kelvin. And to protect it from the sun, it has an extremely lightweight sun shield, which is made out of 5 polyimide aluminium layers. And each of these layers is also spaced. So you have one layer, I think 10 centimeters just space, and then another layer. And then it reduces the heat so that at the last layer you have very little thermal influence on your measurements. And this layer is exactly the system that we use. So you have 50 microns, so about a hair thick of polyimide, and this is then coated with 150 nanometers aluminium.
Could it be used also for other things?
Yes, so if we want to think more towards like earth-based applications, you could go towards flexible electronics, for example. And it's a great model system because aluminium has very comparable mechanical properties to a copper. So if you want to use a copper, you can first figure out your like system properties using aluminium because it's much cheaper.
So can we then straightforwardly use the knowledge you gained for the aluminum polyimide system also for general metal polymer systems? And are you working this direction?
So we are working on half of the problem. So if you look at aluminium polyimide as your model system, you have a metal, right, and a polymer. And why these two work so well is because the polyimide has functional groups that our interlayer can attach to. So our interlayer deposition is a chemical process, right? So it needs some sort of chemical groups it can attach to. What we did now is we switched out the polymer to different polymers, and we also see improvements. So this is certainly transferable. We haven't yet switched out the metal, but I'm quite positive that it can work. Maybe a main challenge with this is that it's not as chemically similar. Like what we currently use as our interlayer, I haven't talked about this yet, is aluminium hydroxide. So of course, this is more chemically similar to aluminium than copper, for example, but it should be comparable.
So for your intermediate layer, it is important to use aluminum hydroxide?
It's just important that this interlayer is amorphous because in the literature, you do have adhesion interlayers. So for example, if you sputter molybdenum onto some flexible substrate, it will not adhere well. So you need a chromium interlayer. However, this interlayer is crystalline and it improves your adhesion. So your molybdenum will no longer delaminate. However, it improves the adhesion too much, so it will crack instead. Mm-hmm. So we take this interlayer concept and we just make it not a crystalline interlayer, but an amorphous one.
So for this intermediate layer, which properties do you have to select in order for it to be, a stable compound?
That's a very good question. I would say crystalline structure, mm-hmm. So amorphous, and also layer thickness, because essentially we do deposit, like whether we deposit an oxide or a hydroxide, that's not a very big difference, but the layer thickness plays a strong role. Like from a certain layer thickness, you actually get brittle properties instead of ductile ones.
Why is it even important to find a strong bond between a metal and a polymer quite generally?
Because if it's weakly bonded, it will delaminate. If you look at, for example, flexible electronics applications, you will deposit several layers if you want to make microelectronics for your phone. And these depositions have a lot of thermal cycling. So you will heat up and cool down again. And a polymer will expand and contract much more than a metal. So if it's very weakly bonded, the interface will no longer be stable.
You mentioned that before, so the experimental technique that you use for this deposition with the electric fields from a gas, right? So are we right in saying that you're an experimentalist?
Yes. Uh-huh. Only by a definition of not doing theory. However, I would describe my thesis as at looking for mechanisms that happen in our system. So I don't have a lot of different systems, but the ones I do have, I investigate very thoroughly and try to understand them.
For this application you mentioned before in the context of electronics, one important property is also that I assume thin metal film does not rip, sort of, right?
Yes. So cracks, I mean, electronics, you need a very good conductivity, right? And you lose your conductivity if your resistance increases through defects in your material. So if you have cracks, then you will no longer be able to conduct. It's very important to preserve your electrical conductivity during straining or also during these thermal cycling deposition cycles, because it is essentially the same thing. Our material will expand and feel some stress, and it doesn't really matter whether we apply it thermally or via pulling on it.
How small can you go? Meaning, like, if you have, say, your compound, can you also scale it down? Or is it difficult?
The PVD that we use is essentially limited to 1 to 2 nanometers, I would say. Our atomic layer deposition is, since it's a chemical process, we can do it layer by layer. And one layer for alumina is 0.14 nanometers. We still cannot enter the quantum realm as you guys do, but...
Just a comment in any case, like, we do it in theory, so...
It's true.
When you do experiment, I guess you have to define some value at which the conductance is not sufficient anymore for the dedicated application, I guess. And I also assume just having one small crack will not incapacitate the device. So can you tell us more about this?
Yes. So now I can actually talk about my experiment that I do. So far, I only told you about what I deposit. So I have this flexible polymer substrate, then I have my interlayer, and then I have my aluminium thick film. Just for reference, the only thing I change is the interlayer thickness, and I keep both metal and polymer thickness constant. So we then take this and we strain it. So we do tensile testing, and we do it in situ. So while we strain, we look at it via an X-ray beam. So we can directly assess our strain and stress in our metal layer. This is a microscopic measurement because we look at individual grains. And then we can correlate this with macroscopic strain of our polymer substrate. And since we assume that our polymer substrate transfers all of the strain to our metal thin film, we can make a very nice stress strain curve. Okay? So this is our key measurement. However, it doesn't answer your question, which was about electrical conductivity. We combine this X-ray beam tensile testing setup with an in situ resistance measurement. So we actually have a 4-point probe, which sounds very fancy, but we just have our sample and we glue some copper wires to it. It works, I promise. And then we measure our resistance change. So your resistance will naturally increase as you change the geometry of your sample, because your thin film will get flatter. But as soon as you get some cracking, your resistance will increase even more. So this has been shown in literature that as soon as you see the first cracks appearing, you get deviation from your expected resistance. And then you can define this as the crack onset strain. And this is the main parameter that we use. And then you can also say, okay, so we get some cracks here. However, it still works. And then you can say 10% from this crack onset strain is our electrical failure strain. So after this, you will not be able to use your device anymore. And we have shown that if you introduce an artificial ALD interlayer, you can essentially double your crack onset strain. If we then look at our sample after testing, more experimental things, you can see how the cracks look, how long they are. And if we introduce our interlayer, we have 10 times shorter cracks. So we do get them. However, they are very short and also angled, so that you still have paths for electrons to percolate through your material.
How long does this process, does this measurement take? So how much time?
So the actual straining is not the time critical thing. However, the XRD measurement, so we do it at the synchrotron, which is a X-ray light source. We have to get a good strain measurement of our aluminium thin film. We need to rotate our samples. So we tilt it from flat to almost 90 degrees. And at each step, we take a measurement. And this tilting and changing of geometry is a time consuming factor. So one measurement takes about 3 hours. Essentially, if you do synchrotron measurements, you make your samples very hectically in the 2 weeks before the beam time, because usually nothing works. And then it finally works and you're like, okay, I don't have to cancel. Amazing. So you already spent 2 hours day and night in the lab. Well, not night, but certainly weekends. Then you arrive at the synchrotron and then you do some night shifts, some day shifts. It hopefully works. So you have a very intensive but nice week of measuring. And then you spend half a year evaluating your data. So this is why I kind of laughed at the idea of being an experimentalist, because I spend a lot of time looking at Excel files.
Normally we go what do you like about your job?
The Excel files.
The Excel files.
Yes. I really like that, every day I face a new challenge. No days are the same. So I can if you like this sort of work life that you get new things every day, I can definitely recommend doing a PhD. I do many different things. I also actually really like writing and putting my ideas onto papers. And if I had to name the thing I like the most is having great scientific discussions with colleagues, and also very flexible and generally very nice work environment.
So in parallel to your work as a scientist, you also are a very passionate singer, right? Can you tell us about this and how you balance both? Because singing itself is already a very time-consuming hobby, I guess.
Thank you. Yes, so my work-sing balance. Thank you for asking this. Actually, Daniel is one of my most loyal fans. He comes to all of my performances. Thank you very much to you. I started singing when I came to university. So it was a very technical university, and I was a bit... I don't want to say shocked, but it just wasn't my world so much. So I needed something else. And I found out that I'm fairly good at it, or at least I have a nice voice, and then I need to train everything else. And it's, I don't have to invest so much time, I would say, as an instrumentalist, because if you play piano, you have to practice 6 hours a day. And this, of course, I wouldn't be able to do, right? So I do maybe 1 hour of practice 5 days a week. And it's very nice. It actually also scientifically opens some doors for me, because people remember me as the opera singer. And of course, I don't do it for this, but as a nice hobby. And also it really helps me to turn off my brain and think of other stuff, and then I'm more relaxed, so I can find more solutions to my scientific problems.
Thanks so much for this insight in the other side of your life, let's say.
Thank you. Thank you.
I think on this note we can end the episode. Johanna, thank you very much for your enthusiasm and for being our guest. Thank you.
Thank you.
Thanks.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.